kind of attacks can happen as a result of that. And we'll also be covering the mitigations for them. A brief introduction about myself. My name is Samit. I work for the product security team at Citrix. I'm a web and mobile application security enthusiast. I've spoken at a bunch of conferences of late, including DEF CON China, Black Hat Asia, AppSec USA, Code Blue, and some more in the past. So for those who do not know OAuth, OAuth is basically it's an open standard for token-based authorization. And basically, as an end user, you can authorize a third-party application to access the resources on your behalf. We'll be covering why OAuth came into being. We'll also cover the flow in a nutshell, and various terms that I'll be using across the presentation. And obviously, the grants that OAuth provides. There are 4 different grants. We'll be covering 2 of them because those are more relevant for the current discourse. And OpenID Connect, which is basically a byproduct of OAuth, and it is used for authentication, whereas OAuth is used for authorizing clients. We'll be covering these attacks and the mitigations for them. And finally, a short Q&A session. Some disclaimers. Ideas presented are personal, not speaking on behalf of my employer. Some content has been borrowed from Brian David Campbell's slides on OAuth 2.0 and mobile devices, OAuth 0, and RFC documents on OAuth. Humor is mine. If you like it, drop me a mail. If you don't, you can blame Security Fest for it. All right. I also have references to Avengers Infinity War, but no spoilers for Avengers Endgame. So if you haven't watched Endgame, you're still good. But if you haven't watched Infinity War, then you deserve the spoilers. OK, so why OAuth? So consider this scenario where LinkedIn wants to access your contacts from Gmail. And in order to do so, it prompts you for your password on LinkedIn website. Now, this clearly raises eyebrows, and it's suspicious, because LinkedIn, you can't really give your credentials to a third-party application. So the problem here is that LinkedIn, with your credentials, can do far more than just access the contacts from Gmail. There are other drawbacks as well. LinkedIn would be required to store your credentials, which is again a no-go. Google will be required to save your credentials, will be required to support password-based authentication. And access cannot be revoked from one single third-party application without revoking it from all the third-party applications. Because the access is based on your password, and if you change your password, it gets changed for every third party. So this is where OAuth came in, and it devises a mechanism for providing LinkedIn, in our case, to just access the contacts on behalf of the user from Gmail, and nothing else. So it's a protocol for delegating authorization, supported by web, mobile, and native applications. An access grant to a specific third-party application can be revoked. And the scope of access, or the permissions, can be constrained. It also avoids sharing of your credentials with the third-party application. And as I mentioned, it also sets a base for an authentication protocol called OpenID Connect. So before we move on to the flow, I would want to introduce the various entities that are typically involved in an OAuth setup. Firstly, the resource owner. This is the guy who is going to grant access to the third-party application to access the resources on its behalf. This is generally the end user. And finally, this one is the application or the relying party or the client. All these 3 terms are synonymous. And this will be the application that is requesting access to the protected resources on behalf of the user. Then the resource server. This is the server hosting the user's resources, which is Gmail in our case. And the authorization server. This is a server that authenticates the user and generates an access token when the user approves of the authorization. This was Google in our case. And finally, the browser. So all of these entities will be used on the next slide. Not this one, on the next slide. So this one is a mandatory step that is required for the authorization server to know who all are the clients that are going to request authorization. So client registration needs to happen as a step before the OAuth exchange happens. So in order to register your client application, you provide your application name, website, logo, and a redirect URI. The redirect URI is used by the authorization server to redirect the auth code and the access token. And after you register, or you register the client, you get a client ID and a client secret. The client ID is not sensitive information. It can be made public, whereas the client secret has to be kept confidential. And in case an application cannot keep the client secret confidential, it should avoid using the client secret completely. And this happens in case of single-page applications or native applications, because the applications can be reverse engineered and the client secret can be extracted from them. OK, so the resource server is there, and the relying party or the client is Stack Exchange in this case. And we also have Google as our authorization server. So when the client needs to request authorization, or the relying party needs to request authorization, it shows a prompt saying sign in with Google or sign in with Facebook. Let's say you chose Google. The client will generate an authorization request, and the browser will get redirected to Google's authorization page, which is where the user will enter his credentials, approved of the authorization. And that is when the auth code gets generated and sent back to the redirect URI. And the redirect URI is obviously Stack Exchange's redirect URI. On fetching the auth code, the relying party exchanges this auth code for an access token by hitting the authorization server's token endpoint. And once it receives the access token, it can fetch the resources on behalf of the user. So that covers like the OAuth flow in a nutshell. We'll be talking about it in more detail as we move ahead. So the only difference between OAuth and OpenID Connect is that OAuth is for authorizing or sharing resources, and OpenID Connect is meant for authenticating the user. So the access tokens are consumed by the resource server because they prove authorization to the resources. And the identity token is consumed by the client in order to populate the UI stating that this is the user who's authenticated. So the flow entirely remains the same. The only difference comes into the last step, where you get an access token. And in addition to an access token, you also get the identity token. Now, this identity token is consumed by the relying party, and it is not sent to the resource server. Access tokens are generally opaque, and they are also called bearer tokens. So when I say opaque, it means that they don't have a structure to them. If you try and decode them, it will not make any sense. It just informs the API that you're hitting that the bearer of this token has been granted access to this API. Whereas identity tokens are JOT tokens, and they have a structure to them. If you decode them, they will comprise of claims. So the claims are nothing but statements stating the identity of the user. And as I mentioned before, the JOT tokens or the identity tokens will be consumed by the client application. JOTs are self-contained. There's some more information on JOTs on this slide. So JOTs are self-contained, which means that you can verify the authenticity and integrity of the JOT that is coming to you without referring to another third party. The reason for that is that JOTs are signed, so you can actually verify the signature and validate whether their integrity is intact. They comprise of 3 components. One of them is the header, then the payload, and the signature. The header portion comprises of mainly the algorithm used for hashing the payload and what kind of token it is. The payload contains these claims, which we saw on the previous slide. And the signature part just mentions the hash of the payload and header. All right. So in the authorization request that the client makes to the authorization server, the client embeds some scopes, which is basically permission that it is requesting. This may be like, it might request the email of the user or the profile of the user, so some data regarding the user. And once the user approves of these scopes, in the identity token that is generated, these claims are embedded by the authorization server. These claims are also available at the user info endpoint on the authorization server. So the client can actually request for them. And scopes allow applications to request delegated access. So basically, if you have a scope saying mail.read, the application is requesting read access to your mails. And the authorization decision basically is made by combining 3 entities, which is the mail, the permission that you're granting, who's the user for which the mail belongs, and the entity that is requested, which is the mail in our case. So if you have mail.read permission, only the mails of user, who is the red one, will be accessed. And if there is some other user's mail, they will not be accessible to this particular client. Coming on to the various grant types, there are 4 of them. One is the authorization code grant, another one is the implicit grant, resource owner password credential grant, and client credential grant. All of these are used in different situations or scenarios. We'll be covering the first 2. But before we start with them, I'm introducing the real actors. Small analogy. Our resource server will be the soul stone. And obviously, Red Skull right now possesses that soul stone. So he's the resource owner. And Thanos wants it. And this is the application relying party or the client. And Gamora will be our authorization server. So Thanos tries to access the soul stone directly, and he gets an unauthorized response. And it asks the resource owner for giving him approval by redirecting it to authorization server. So you get redirected to the authorized endpoint on the authorization server, and the user then approves of the authorization, and that is when you get the auth code back, redirected to the application. So Thanos has been authorized to access the resource server now. But there's one additional step in the auth code grant flow, which requires you to exchange the auth code for an access token. And for this, the client needs to authenticate to the authorization server by using the client secret and the client ID. So that's where the client ID and client secret come in handy. And once you hit the token endpoint with the client secrets, the token is generated by the auth server and returned to the client. The client can then access the resources with the help of the token embedded in the header. So Thanos finally gets the soul stone. He's happy. So what are the benefits of the auth code step? You could have directly returned an access token from the auth server. But the auth code actually helps you to provide the ability to authenticate the client. So even if the auth code gets leaked, it cannot be exchanged for an access token by an attacker. The attacker needs to know a client secret, and that is when it can exchange the auth code for an access token. Additionally, auth code gets exposed to the browser in the URL when the redirection happens. But access token is returned in the response body by a server-to-server call from the auth server to the client. So therefore, it avoids the leak of access token via the browser. Auth code grants are frequently used for web applications, so that's their use case. And if you see the traffic, it would look something like this. This is the authorization request, and it comprises of the authorization server's FQDN, followed by the authorized endpoint, and then the response type, which is set as code for ACG, which is authorization code grant. And then the client ID and the redirect URI, where the authorization server will redirect the auth code. And in the response, the auth code is being redirected to the client with a state parameter, which is used to avoid CSRF attacks. We'll come to that. And when you hit the token endpoint with this auth code, you're also supposed to specify the client secret. So this is the client making the request. It can send its client secret with the auth code. And that's when the access token is returned. And is returned to the redirect URI again. All right, the second of them, implicit grant, pretty much alike auth code grant, but with the difference that the auth code is not generated and is not sent back to the client. Or instead, a token is directly generated and sent back to the client. Thanos still gets the resource, so he's happy. So if you see the traffic, it would look something like this, where you have the authorized endpoint being hit, again with the same parameters, and then you get back an access token directly. So implicit grant was earlier used for single-page applications and mobile applications or native applications. But of late, everybody is recommended to use auth code grant without the client secret for native applications. So this slide summarizes which grant to use in what scenarios. So as I mentioned, implicit grant was used for single-page applications earlier, even for native applications. But nowadays, we're using ACG with an additional layer of defense in depth called PKCE, which is proof key for code exchange. And we'll come to that. We'll cover PKCE as well in the slides. The rest of the two grant types are used in these cases, which we'll not cover right now because we have a shortage of time. So next up is OIDC, OpenID Connect, in context of native applications. Overall, the steps remain the same. The only nuance that comes into play is when the auth code needs to be redirected to the native application. And since the native application is running on the mobile device, there is another attack surface that gets exposed because it's not a server-to-server call. It's like more of a untrusted device where the auth code has more chances of getting leaked. So first step, users need to access some protected resource. So the client opens the browser, redirects the user to the authorized endpoint. And once the user signs in, the user is asked to approve of the request made by the client. And once the user approves, the authorization endpoint generates an auth code, and it needs to send it back to the native application. And for that, the browser has to do an HTTP redirection to invoke the native application with the auth code. And that's where you have to register callbacks. And if you see here, the application has registered a custom URL scheme, xcom.mycorp.myapp. And when the browser receives the auth code on this scheme, it knows which app to invoke because the application has registered for this custom URI scheme. And that's done this way. So for Android, in the manifest file, you can define the URI scheme. And whenever the browser receives this custom URI scheme, it will redirect it to the native application, which has registered for this scheme. Once the application receives the auth code, it can exchange it with the token endpoint. And it will get back the bearer token with the refresh token as well. And then the application can use this bearer token to access the resource, which is the API here. By embedding, this is done by embedding the bearer token as an authorization header. So if you see here, there's the authorization header with the bearer token embedded. So that brings us to a first attack scenario called authorization code intercept attack. And the preconditions for this attack is that the authorization code grant is used. And in native applications, the client secret is not used because native applications can be reversed and you can get the client secret. And the attacker manages to register a custom URI scheme by using a malicious application on the same device. So this custom URI scheme was supposed to be used by the legitimate application, and the attacker has registered for that callback with his malicious application. So you can see where this is going, because once the authorization code is returned in step number 3, the browser will, because of the HTTP redirection, it will try to invoke the legitimate application with that auth code. But since the malicious application has also registered for that custom URI scheme, the attacker gets the auth code using his malicious application. And once this auth code reaches the malicious application, the attacker can redeem this auth code for an access token by hitting the authorization server's token endpoint. And obviously, it becomes utmost important to handle these redirections carefully. Instead of using custom URI schemes, which is this, there is no naming authority for them. So basically, any malicious application can register for the same custom URI scheme as the legitimate application. So instead, one should use claimed HTTPS scheme URI redirection. So the scheme remains HTTPS, followed by the FQDN under the control of the application. And this is where the identity of the destination application is guaranteed to the authorization server by the operating system. No other application can register for the same FQDN because it is owned by one particular client. Which brings us to PKCE, which is pronounced as PKCE, and it's called ProofKey for code exchange. So PKCE adds some elements to the regular auth code grant flow to ensure that even if your authorization code gets leaked, an attacker cannot exchange it for an access token. So in addition to in the authorization request, what the client does is that it generates a code verifier, which is nothing but an alphanumeric string kept confidential with that particular application, which is generating it. And it generally takes a hash of it, which is called the code challenge, which is symbolized by T, followed by whatever code verifier it is applied on. So that's the hash value of code verifier. And then you're supposed to send the code challenge method, which is the hash function you've used over the code verifier. So basically, you're sending the hash value here. The authorization endpoint stores that hashed value with it. And then it redirects the browser to the client with the auth code. And this can be intercepted by the malicious client. So the malicious client is having the auth code now. So in request number C, where you have to exchange the code for the token, the legitimate client needs to send the code verifier, which is the unhashed value, the message that is which is hashed. So the code verifier is not known to the malicious application. And that's what provides the security here. Basically, the token endpoint will receive this code verifier, hash it again using the same code challenge method, and then verify whether the value matches the code challenge which was received earlier in the request B. And if it does, only then the access token is sent back. Otherwise, it's not. So this is a small and sweet demo of faulty PKCE implementation on Microsoft IDP. And here it goes. So if you notice here, I have these last three requests, one of them is going to the authorized endpoint, the other one is going to the login endpoint, and the third one is going to the token endpoint. So the request that goes to the authorized endpoint has the redirect URI. Yep. So if you notice here, there's the redirect URI of the native application, and then the code challenge, which is the hashed value of the code verifier, and then followed by the code challenge method. Then I'm redirected back to the login page, and I send my credentials, and then the server, when it receives that login request, it generates an auth code for me and redirects the auth code to the native application, which is happening here. So you're getting redirected back to the native application with the auth code. And finally, the native application, when it receives the auth code, it hits the token endpoint with the code verifier and the redirect URI and the auth code. So just sending it to the repeater, trying it out, and since it has the auth code and the code verifier value, I get back the identity token, access token, and refresh tokens in the response. But the problem with Microsoft's IDP was that it wasn't validating the code verifier here. So even if you remove the code verifier completely, you still get back the valid access token, identity tokens, and refresh tokens. And since there's no client secret involved, if your auth code gets leaked through the same attack that we saw earlier, this can result in a malicious application redeeming your auth code for access tokens. So the RFC on PXE actually mandates that all native applications must implement PXE, and all the authorization servers must support PXE in order for the applications to use it. But Microsoft clearly wasn't validating the code verifier, which resulted in many native applications being compromised, which were using the same endpoints, login.microsoftonline.com. And then we have the Crosssite request forgery on the client redirect URI. So let me explain this with the help of a flow diagram. So we have the attacker here who's publishing a malicious website, and the user or the resource owner happens to visit this malicious website. The malicious website then generates a forged response with the attacker's auth code in it. And what happens next is that the client will try to exchange this auth code for an access token with the auth server. And it gets back the attacker's access token instead of the legitimate users. So basically, if he accesses the resource, he'll get back the attacker's resources instead of the user's resources. So this is like a login CSRF, which happens with OAuth flows. So there are two mitigation strategies for this. One is to embed a state parameter in the authorization request. Since there is no authorization request, the attacker has no way of knowing the state parameter, and it has no way of adding the state parameter in the response to the auth request, which is this one. And the client needs to validate whether the state parameter is present and if it matches the one that was sent in the auth request. And that's how the attack will get detected. The second way to do it is using origin header check. Because the malicious website generates this authorization response, the client can check what kind of origin this response is coming from and then take a decision whether to proceed to exchange the auth code for an access token or not. And the most commonly found one is open redirects on the client. There are a few assumptions here. So we're using the implicit grant. Just for convenience, it could be Auth Code grant as well, but just to show the flow in a simpler way, I've considered using the implicit grant. And the client registers a redirect URL with the pattern client sumsite.example/cb ? So clearly, there's a wildcard at the end, and the attacker can actually add anything to it. Additionally, the client is exposing open redirects using the redirect2 parameter. So all that the attacker needs to do is trick the victim into opening this malicious website, evil.example. And from evil.example, the attacker can initiate an authorization request with the redirect URI specified as client sumsite.example, which is exactly matching this, /cb with a redirect to client.evilexample/cb. So since the client is exposing this open redirector, what will happen is that once this request reaches the auth server, the pattern matches because there was a wildcard at the end. We've just added a redirect2 parameter at the end, so it matches. And the auth server is going to redirect you back to the client with an access token, which is here, present as a URI fragment. And once this response reaches the client, since it is exposing an open redirect, it will redirect you to the client evil.example. And the way browsers behave is that if this redirect does not contain any URI fragment, the browsers will attach the URI fragment from the previous response and append it to client evil.example. So that's how browsers behave. They try to tag along more information to whatever you're accessing. So they will naturally, or inherently, add the access token URI fragment to this particular domain, which is the evil domain. And that's how your access token could get leaked. So if you're using Auth Code grant, and the same situation is there with the same assumptions, you could end up leaking your auth code instead of the access token. So let's say that the client.com was exposing this open redirect with the parameter redirect URL, and it had an integration with Google Drive. So when you hit this particular endpoint, you're redirected to Google Drive to authorize the client to access your Drive resources. And once you authorize, the client redirects you back. So the auth server redirects you back to the client, and since the client is exposing the open redirect, it will redirect you to attacker.com with the auth code appended to it. So as a mitigation, clients must not expose open redirects. That's the best case. Clients must memorize which auth server they sent an auth request to and ensure that any subsequent requests go to the same authorization server. Clients should use ACG, which is the Auth Code grant flow, so that even if the auth code gets leaked, there is still a need of the client secret to be present in the next request. So the attacker who gets it needs to know the client secret to exchange that auth code for an access token. So small joke on Thanos again. Thanos is our client who has exposed the open redirects. And this is the dialogue between Gamora when Thanos snaps his finger and returns. All right. So phishing using user trust in auth servers. So this is a simple example, pretty straightforward, where you are misusing the trust that the user has in authorization server. So what you're going to do is you can register, or an attacker can register with the authorization server with this particular redirect URI. So basically, he's registered a malicious client on the auth server. And then it can send a forged URI to the user. Since the URI has authorization server's FQDN, the user will trust it. And he may click on it. And if he does, what will happen is that the scope here is an invalid scope. So the authorization server will basically generate an error and it'll redirect you back to the attacker's domain, because that is where the request is coming in from. And that has been mentioned here in the redirect URI. And since this redirect URI is already registered on the auth server will think, OK, I can redirect you back to the client, but still, I'm not going to give you anything else. I'm not going to give you auth code, but I can still redirect you. So you're eventually going to get redirected to attacker.com without the auth code. But then you can do a lot of phishing attack, because the user thinks he's visiting auth server, and he eventually ends up on attacker.com. So AS authorization server needs to take a call whether to redirect or not. And he may choose to inform the user about the redirect. And that's the only way the user can save himself. OK, then the mix-up attack. This attack happens in scenarios where the client interacts with multiple authorization servers. And one of them may go rogue or turn malicious. And the goal is to obtain the auth code or access token by tricking the client or the application to sending it to the attacker-controlled auth server. Two preconditions. I'm going to use ACG here, which is the Auth Quadrant, but it applies to implicit grant as well. And the client is using multiple auth server. That's the only precondition. And the other one is about that the client is using the same redirect URI for all the authorization servers. So the redirect URI is not authorization server specific. So I'm going to take the example of two AS authorization servers. One is Google, one is Facebook. And let's just assume that Facebook goes malicious. No offense to Mark Zuckerberg or Facebook. It's just that Facebook has been in news of late. And let's see the flow using this diagram. So what happens is that, let's say LinkedIn shows you that you can log in through Facebook or Google. And the user chooses Facebook. So the authorization request is generated to Facebook's auth server. And Facebook, since it's malicious, it'll redirect you to Google's auth server. So you're shown the Google's auth server page instead of Facebook. That's the only place where the user can get to know that there's something going on. But if the user doesn't pay attention, then he may authorize the request, and an auth code gets generated and is redirected back to the redirect URI of the client. And the client still thinks that the authorization request was initiated with Facebook. So it will try to hit Facebook's authorization server to redeem this auth code. But once Facebook gets the auth code, it will try to redeem it at Google's token endpoint and get back a token for the user. So Facebook can now use that token to access victims' Google's resources. So the idea here is the auth server could actually return an issuer parameter so that the client knows that the auth code that it is receiving is not from the intended auth server. So in our case, the issuer would have been Google, because that's the entity that was generating the auth code. But the client thought that it is initiating an auth request to Facebook. So that's where the attack would have got detected. Alternatively, the clients could use authorization server-specific redirect URIs, like so. Client.com, Google redirect URI, client.com, FB redirect URI. And the client, when it initiates the auth request, it knows that it's Facebook that it's redirecting to. So the auth code should come back to Facebook's redirect URI. But if it comes to Google's redirect URI, then obviously there's something fishy going on, so the client will probably detect it. And then finally, I thought I'll give you some defense in-depth tips so that you can reduce the damage even if your access tokens or auth code is getting leaked. So what if your access token gets leaked? What can you do best? can you still reduce the damage? So there are ways of tying the access token to the audience, which is the resource server. So you can have access tokens mapped to be used only to certain resource servers. And that's called audience-restricted access tokens. There are multiple ways of doing it. I can't really cover them here because of the shortage of time. But you can read about it on the RFCs that I have in the references. The other thing that you can do to avoid the misuse of an access token by an attacker is that you can map it to the sender. So basically, these are called sender-constrained access tokens. So when you're generating an access token, when your auth server is generating an access token, it binds this access token to a specific client or the application. So even if that access token gets leaked to a malicious entity, it cannot access your resources. So again, there are multiple ways of doing it, but you can always read about it. I am not going to cover this right now. What if your auth code gets leaked? So maybe you can have the server, auth server, implement a one-time usage restriction for your auth code. So if, let's say, your auth code gets leaked, the legitimate application uses that auth code, and the malicious application also uses that auth code. So what the server can detect this, obviously, because it is receiving 2 different requests with the same auth code. And once the server receives 2 different requests, what it can do is that it can invalidate all the access tokens that were generated with the previous auth code. The other thing that the auth server could do is that it can bind the authorization code to the redirect URI. So once you hit the authorized endpoint of the AS, the auth server maps the auth code it generates to the redirect URI. And once the attacker tries to redeem the auth code, the server needs to check whether the access token that it is sending to the redirect URI needs to match the auth code's mapping before it did. So basically, you have a mapping of the auth code and the redirect URI, and the server needs to validate whether the request coming in is actually, in the request that is coming in, the redirect URI is matching or not. So you can have the auth code bound to the redirect URI. If you happen to use implicit grant and your access token is getting leaked in the browser's history, avoid using redirect-based access token, returning the access token. You can actually use form post response methods so that your access token is not exposed in the URI. Also, you should avoid using 307 temporary redirects. That's a no-go for sure, because your credentials may leak to the client. And more on it at this particular RFC. You can have a look at it. All right. These are some very important references that you should go through. And if you want to implement a perfect OAuth solution, I know it's a huge list, but that's what things we do for security. All right. So, oops. All right. So that brings me to the end of my talk. And here's some contact information, just in case you'd like to drop me a message. Thank you for your attention. And that's all. I'm up to take questions.
All right. Let's see. Thank you. That was a great talk. Let's see if we have any questions in the crowd. Any hands up? I know you're getting a little bit tired, but come on, guys. There must be one question. There's probably candy in it for you. Really? You covered everything, man. This is amazing. They should hire you to do this kind of stuff. So no hands up. Well, I'm sure you can get in touch with you on Twitter or email if they have any questions afterwards, or during the party, of course, which will happen after the next talk. So thanks again, Samit. That was great.
Thank you so much, Juan.